Swayam Prabha. Digital India. Educated India.
We continue our discussion on clean steel. We have seen various aspects of clean steel and its relationship with the inclusions. Now, not all sizes of inclusion they are harmful. In fact, the size of the inclusion which can be tolerated will depend upon the particular application. That means there is a critical size below which the inclusions are harmless, but above which they will be harmful. So, I will give some applications and the tolerable size. For example, steels for line pipes, the tolerable size is 100 micron meter. Then for bearings, the tolerable size is 15 micron meter. Then tire cord 10 micron meter, heavy plate 13 micron meter, and wires around 20 micron meter. So, these are the critical sizes. There could be several other applications which can tolerate some minimum size, and hence the size above that should be removed, but below that if it remains in the steel it does not harm the property. Now, say the impact property will depend upon whether inclusion is brittle or ductile. Low deformability, it affects hot working, because if the inclusion is non-deformable, then during deformation processing it will break because load is applied. As such, macro inclusions are harmful. Inclusions that have lower coefficient of thermal expansion than matrix set up stresses in the matrix and cause fatigue failure, and these effects we have already seen just in our previous lecture. Now, method for evaluating cleanliness of steel. Methods for evaluation of steel cleanliness. So, there are several methods through which one can assess the number, size and size distribution of inclusions. So, first method is, say I will classify them direct method and indirect method. Among the direct method, one is metallurgical microscope. Metallurgical microscope. That means take a specimen, polish it, and it is seen under the microscope, and the microscopic analysis can tell the number, size and size distribution of inclusions. Another important is the image analysis. Now, there are packages and softwares are available which can analyze the image for the inclusions. Third method is sulfur print. Third method is sulfur print. Sulfur printing is taken and one can also see what is the inclusion over there. Still another method is electron beam melting. Electron beam melting. in the electron beam melting, sample is melted under vacuum by electron beam and inclusion floats, and from there one can find out what is that inclusion. Another still direct method is scanning electron microscope. Scanning electron microscope. In this particular method, the importance is sample preparation, and sample can be seen under the scanning electron microscope, and the image it can be analyzed for the size, type and size distribution of inclusions. Another method therefore indirect method. Say in the indirect methods, one can determine total oxygen, and from the total oxygen and the presence of oxide forming element one can determine the approximate number of inclusions. Also one can do nitrogen determination, and from there one can determine the number of inclusions. So, these are the methods for evaluation of steel cleanliness. Now, it is important to know the sources of inclusion. Say, what are the source of inclusion? Source of inclusion. Now, here it is to be noted that inclusion does not form in BOF steel making, that is during conversion of hot metal to steel, inclusion in BOF converter they do not form. Equally they do not form in electric arc furnace steel making. Equally they also do not form in energy optimizing furnace. So, the formation of inclusions occurs at two sources. One, during transfer of steel, during transfer of molten steel from one vessel to another vessel. For example, when BOF steel or electric arc furnace steel or EOF steel is tapped, then a tapping stream is a source where atmospheric oxygen can be entrained and it can cause inclusion formation. Then from ladle it goes to secondary metal processing operation, then from the secondary metal processed steel which is again contained in the ladle, then it is transferred to the ton dish. So, during the various transfer operation that takes place between the tapping of heat from the primary vessel, which is either BOF or EAF or EOF, and to the casting stage. So, several transfer operation they occur under the atmosphere, which causes oxidation and hence the formation of inclusions. Another source of inclusion is during solidification. During solidification, because when steel solidifies, then the impurities are rejected into the liquid because of the low solubility of that impurity in the solid. So, accordingly, depending on the concentration of impurity and depending on the partitioning of solute element between solid and liquid, the formation of inclusion can also occur or does occur during solidification of steel. In fact, this during solidification it occurs which is called precipitation due to reaction from molten steel or during solidification. Another source of inclusion is that right from BOF to continuous casting or ingot casting, the molten steel is contained in the refractory lined vessel. So, the mechanical and chemical erosion, of refractory, that will also lead to formation of inclusion. Then as I already said, oxygen pickup during transfer operation, Now, if we want to identify the location, then possible locations are furnace, tapping, that is so called tapping stream, then ladle, teaming, that is the teaming stream, then pouring stream, then mold, or also they can occur during heat treatment and rolling operation. So, these are the subsequent locations where molten steel is handled, except in the last stage during heat treatment and rolling, where solid steel is reheated to around 1200 degrees Celsius to create the different properties. So, there also the oxidation can occur, and hence some sort of inclusion formation can take place. During solidification, the inclusions which are likely to form, that will depend upon the concentration of the impurity and the partition coefficient of that impurity. Normally oxides, oxysulfides, nitrites, carbonitrides, they can form during solidification. Now, once you know these are the sources of inclusion, then how to control the inclusion formation? So, obviously the next important thing which is important is control of inclusion. Control of inclusions. Now, a clue for control of inclusion will come from source of inclusion, that is from where the inclusion comes, you control it. So, inclusion will not be entering or will not be forming during the subsequent stages. So, as such, what will I do? I will try to make a flow sheet to explain the control of inclusion. Say one source we have seen tapping, so I will put the control of inclusion can be done during tapping. Also it can be done during teaming. So, you have seen that tapping and teaming, they are the two operations that are carried out between primary steel making unit and the casting unit. So, in between several operations are going on which lead to the formation of inclusions. So, let us see first about the tapping. Now, tapping from either EAF, electric arc furnace, or BOF or EOF, I can also include this in my lecture. So, from tapping, the steel goes from converter or from electric arc furnace or from EOF, it goes to ladle. What happens during tapping? So, during tapping, what can happen is the slag carryover should be minimized. Slag carryover should be minimized. Because whether converter or EAF or EOF, whatever the steel unit be, the steel is covered by a slag. So, during tapping or the carryover slag should be minimized. Why? Because the slag is highly oxidizing in nature. It contains FeO, it contains MnO. So, these oxidizing slag, if carried over during tapping into the ladle, then whatever amount of aluminum that is added into the ladle, it will react with the FeO and MnO of the carried over slag and it will form the inclusions. How it will form? Say for example, if I take reaction say 3 FeO plus 2 aluminum, that will give you Al2O3 plus 3 iron, or for that matter 3 MnO plus 2 aluminum, that is equal to Al2O3 plus. Now, in fact, the presence of FeO is more important because FeO is of the order of 16 to 20%. So, this reaction is more important. So, if you see the stoichiometry of FeO and aluminum reaction, then what it says that 1 kg FeO, 1 kg FeO, if it is carried over into a ladle, then it decreases aluminum. 1 kg FeO decreases aluminum by 62 upon 216 kg, that is equal to 0.286 kg of aluminum. Now, this 0.286 kg of aluminum will form around 0.51 kg of Al2O3. Now, the density of Al2O3, let us take it around 4 gram per centimeter cube, and if all the inclusions were spherical size of 1 millimeter diameter, then from volume you can calculate around 240 inclusions will form just by carrying 1 kg of FeO into the slag. So, my whole idea of calculating this is to emphasize the fact that during transfer of molten steel from converter or electric arc furnace or energy optimizing furnace to the ladle, the slag carryover should be as minimum as possible. Therefore, what is important here, to adopt the method which are called slag free tapping. Slag free tapping. Some of the methods I have already discussed in my BOF steel making lecture. In order to have slag free tapping, in the past so many years, so many methods are being developed, and these methods are in use, like slag cut ball method, stopper method, detection method, and so on. So, these methods allow in fact slag free tapping, and that is an important. Now, another control where inclusion can be controlled is during trimming. There are one is from ladle to another vessel for casting, which is called ladle to tun dish. In this ladle to tun dish, the stream is again, if it is bare, that is not covered by a refractory, then the oxidation will occur. So, here one has to provide the so called shrouding of stream. So, by shrouding the stream from ladle to tun dish, one can control the inclusion formation. Then molten steel is contained in the tun dish, because during the transfer from ladle to casting, for example, in continuous casting, tun dish is the last refractory lined reactor where molten steel is in contact with the refractory material. So, accordingly the tun dish can also contribute to large number of inclusions if proper control is not being done. What is the proper control? Say first, the steel is in contact with the wall, so refractory wall is a source. Refractory wall is a source, that is reaction between dissolved aluminum with oxygen of refractory lining. That is, when molten steel is poured into the tun dish, it has free aluminum also, and if the refractory is unstable, then aluminum can react with oxygen of the refractory lining and can form the so called Al2O3 inclusions. So, it says that the lining of the refractory of the tun dish must be chemically stable, so that no reaction should occur. Another important source which can be controlled, because the tun dish or the molten steel in the tun dish is covered by a flux, The fluxes are used to absorb inclusions. That means, the fluxes should be also molten, so that any inclusion which is rising from the bath of the tun dish should be able to be absorbed in the flux. So, therefore, proper properties of the fluxes in the tun dish is also important. Now, another important property that flux does, it shields the molten steel contained in the tun dish from atmospheric reoxidation. So, it prevent air from atmosphere. So, that means the proper selection of the flux for tun dish is important to control the inclusion formation. Now, next point which can be controlled is from tun dish to mold. Tun dish to mold, because molten steel is poured from tun dish to mold, and there are several places where inclusion can occur. Say first, the deoxidation product which are in the molten steel can be directly transferred to the mold, because mold is used for solidification, and once steel is solidified, then whatever inclusion which has been transferred from tun dish to the mold, it will remain entrapped into the solid steel. Another source is the nozzle clog. Because the molten steel is poured from tun dish to the mold by submerged entry nozzles. Molten steel, if it contains alumina inclusions, then alumina inclusions they deposit on the walls of the submerged entry nozzle. So, sometimes these nozzle clogs can detach from the wall, and they will again be carried over into the mold and will contribute to the formation of inclusions. Now, third way you can control is the entrainment of slag from tun dish. Now, how slag gets entrained? As the casting proceeds, the molten steel level in the tun dish falls during the ladle changeover period. So, as a result of decreasing height of the tundish, a vortex phenomena can occur, and because of the formation of the vortex phenomena, the slag which is present on top of molten steel in the tundish, it may be drained and transferred to the mold, and it may also cause inclusion. So, therefore, to control the inclusion through vortex formation, it is important that a particular height of the liquid steel is maintained, and that is particularly important during sequence casting, because during sequence casting, when the ladle is emptied and the next ladle when it is arriving, the time which is taken by arriving of the next ladle, that is important. If it is properly synchronized, then molten steel from the tundish will not fall to a height where vortex can form. So, this is also an important thing. And other could be the air leakage in the submerged entry nozzle, that is reoxidation product formed due to leakage or due to air leakage from whatever the source. Also, during continuous casting, mold is also covered by the slag. So, it is also possible mold slag entrainment, because sometimes the liquid steel in the mold is stirred for removal of the inclusions or for removal of the temperature gradient. So, in that process of stirring, the slag which is on the top of the mold, it may get entrained and it may be picked up during solidification. Then the precipitation of inclusions, due to drop in superheat, Now, this thing all say correspond to tundish to mold operation. Now, when the superheat drops or when the liquid steel cools, it solidifies, then depending on the solubility limit, the elements in the steel can combine and an inclusion can precipitate. Now, for example, say TiO2 in say titanium treated steel. Now, here the agitation of the bath, say in the ladle or in the tundish, it helps to float the inclusions, and in fact, the ladle or tundish stirring is done to allow the inclusions to float. Now, rate of rise of inclusion, it depends upon the diameter of the inclusion and the buoyancy force, that is the density difference between the steel and the inclusion, and as such the rate of rise of inclusion is given by G d square upon rho s minus rho inclusion into 18 viscosity. Now, if I take rho s, that is the density of steel, as 7160 kilogram per meter cube, and rho inclusion, if I take for example 2200 kilogram per meter cube, then a 5 micron meter and 50 micron meter spherical size inclusion will take 3000 minutes and 50 minutes respectively to float a bath height of 2 meter. So, what is important from here is the coalescence of inclusion is important. Coalescence of inclusions are important. Smaller diameter inclusions, they will take a longer time to float. Larger diameter of inclusions will take a smaller time to float. Anyway, the problem is with the smaller size inclusion. If the inclusions can be coalesced or if they can be agglomerated by creating some sort of agitation condition, then they will become bigger in sizes and their flotation becomes easier. So, these are some of the ways in which the inclusion control can be done, and all these ways are exercised so that one can produce clean steel. Now, enough we have said about the control of inclusions, about the removal of inclusions. We have come to a stage, well, that it is not possible to produce steel without inclusions. That means, inclusion is a part of production of steel. If you want to remove them, a very long time is required in order the inclusions can float. Even then, it will not be possible to get rid of the inclusions which are there in the molten steel. So, what should be done? So, that is where the important is called inclusion engineering. This is what the inclusion engineering is important. Now, in the inclusion engineering, what is done? An engineer, he does not bother about the inclusion which are present, but what he does, he tries to modify the inclusions such that their harmful effects are minimized. Because when it is true that we cannot produce steel without inclusion, and to remove a small size inclusion we require a very long time which may not be economically viable. So, therefore, an engineering aspect of design of inclusion becomes very important. So, in fact, remember, inclusion engineering does not refer to removal of inclusions, but it refers to modify them in terms of chemical composition so that their harmful effects can be alleviated. So, inclusion engineering also involves distribution of inclusion uniformly in the matrix so that composite property of the steel can be utilized. So, what I wanted to say, in fact, inclusion engineering, it does not relate to removal of inclusions, but it relates to modify them. So, it is a practical way of modifying the harmful effects of inclusion into harmless effect or positive effect. If the inclusions can be distributed uniformly in the matrix, then in fact you have produced a material which is a composite material of very different properties. So, in some cases deliberate attempts are made to form very fine inclusions, for example, nitrides, carbonitrides inclusion in hardening steel. Now, such inclusions can form with oxygen, nitrogen, sulfur or carbon by adding elements which produce a very high melting point, for example, by adding titanium, tungsten and rare earths or aluminum, because they will produce a high melting point and that may be beneficial, and in fact that is what is meant under the term inclusion engineering. Remember, the job of an engineer is to modify the inclusions which are considered to be harmful such that their harmful effects are converted either into harmless effect or positive effect. That is what an engineer does. How it can be done? If you just think, then it comes to my mind that one has to be in search of an element that can react preferentially with the impurity and do the job of modification. So, as such, what are the requirements? What are the requirements for an element to be added? For an element, what are the requirements? Say, first requirement of this element should be, it should have high affinity with the impurity. High affinity with the impurity. In fact, it is the oxygen and sulfur, these are the two important impurity in the steel, and we are looking for an element which has a strong affinity with that impurity. However, if other impurities are there and if you want to modify them, we have to find out an element which has an affinity with that particular element. Second, we are looking for that element should able to modify chemical composition. Chemical composition of an inclusion, so that if it is solid at the steel making temperature, it becomes liquid. If you could get that, it is wonderful. Third, if possible, it should be able to modify the shape, particularly I am talking of the shapes like sharp corners, sharp edges which are detrimental to the properties, and those shapes can be converted to spherical. What type of inclusions we are looking for modification? See, what types of inclusions? What types of inclusion that we are looking for modification? Now, for example, oxides and sulfides. So, what type of inclusion we are looking for modification? They are the oxide and sulfide. Among oxide, for example, Al2O3. Now, Al2O3 inclusions are very low deformable and hence they will break. That is not good. Similarly, the manganese sulfide inclusions, if they are rolled, it will form a stringer type of inclusion. So, for oxide modification, calcium is the most effective element. Calcium is the most effective element because calcium has a very high affinity with oxygen. Also, mish metal, which is an alloy of cerium and lanthanum, can also be used, but calcium is more powerful and hence calcium is used for modification of Al2O3 inclusions. How does it? How it does? If you see this phase diagram of CaO Al2O3, which I have sketched for you, on the x axis at this point we have 100% Al2O3 and this is 100% CaO. So, if we add 8% CaO, then the melting point of the alloy which forms CaO Al2O3, it decreases. In fact, if you see the composition corresponding to C12 and A7, that means 12 CaO and 7 Al2O3, its melting point is around 1400 degrees Celsius. Now, note pure Al2O3 has a melting point of somewhere here around 2050 degrees Celsius, which is solid at the steel making temperature. It is very difficult to remove. So, if we do a calcium treatment, then a composition is reached where the melting point becomes minimum, and this composition is 12CaO 7Al2O3. However, there are other compositions are also, for example, Ca, which is CaOAl2O3, Ca2, CaO2Al2O3, all have melting point higher than 12CaOAl2O3. So, it is attempted that by calcium injection a compound forms, that is 12CaO 7Al2O3, which has a very low melting point. In fact, it is liquid and it can be made to float also. So, that is what the important point in case of modification of alumina by calcium. Good, we have got an element. What are the problems? So, the problems with the calcium addition is as follows. Problems: calcium has a density which is 1.55 gram per centimeter cube. What does it mean? It is very difficult to introduce into the melt, which has a density of 7 gram per centimeter cube. It has a boiling point 1492 degrees Celsius. What does it mean? At the steel making temperature, which is 1600, it is in the vapor form, and vapor is highly reactive. Third, extremely low solubility in steel, and solubility is of the order of 320 ppm. All advantages which I have told you about the calcium addition, they have gone now to development of a technology to make calcium available in the steel bath, because if you just do not think about that, whatever calcium you add, it will float, it will all oxidize, it will not do your job. So, it boils down to development of a technology to inject calcium deep into the bath, at least up to a depth where the vapor pressure is, the effect of vapor pressure is minimized. So, for that the question comes the technology, and question comes how to add. How to add? In the form of alloys, calcium silicide, calcium iron, calcium aluminum, these are the alloys type in which it added. Rather, it is added in a wire form, and there is a cored wire in which calcium silicide is filled, and these wires are available in the form of the roll, and this calcium silicide powder is injected at a very high speed, varying from 30 meter per minute to 300 meter per minute, so that it directly enters deep into the bath to counter the effect of vapor pressure, so that at that particular depth calcium remains in the liquid form and it can do the job of inclusion modification rather than oxidizing itself. So, that is where the technological important. Now, another issue is that of the sulphide shape control. Sulphide shape, rather I will say sulphide shape modification. Now, as you seen, the effect of FES is counteracted by addition of manganese, and manganese sulphide inclusions they form, and hence you have alleviated the problem of hot shortness. But manganese sulphide inclusions on rolling, it forms a stringent type of inclusion. So, still you require a modification of this particular inclusion. So, we are looking for an element which again has a strong affinity with sulphur. No doubt calcium has some affinity with the sulphur, but when it is compared with the mish metal, which is an alloy of lanthanum and cerium, the desulfurizing ability of mish metal is higher than the calcium. Now, suppose if we do calcium, then calcium modifies the Al2O3 inclusions and it forms 12 CaO7 Al2O3 inclusions. For example, if this is the inclusion which is C12A7. Now, this 12 CaO7 Al2O3 inclusion has a very high sulfur capability. That means it can absorb sulfur, and on the top of this inclusion one can have the so called CaS MNS on the surface of the 12 CaO7 Al2O3 inclusion, and if we roll it, say on rolling, it does not form a stringent type of inclusion. So, the center is again that of C12A7, and this the on rolling, this one is the elongation which occurs. So, that way the harmful effect of sulfide inclusions can be alleviated. When mish metal is added, then the core of 12 CaO7 Al2O3 can be C2O3 or Al2O3 based upon oxide, while surface can be lanthanum sulfide and cerium sulfide. Now, for desulfurization, it is essential that oxygen content of the bath should be very low, because cerium and lanthanum will accordingly react with the oxygen and they form cerium oxide or lanthanum oxide. So, it is very essential that the bath should be deoxidized and then the mish metal is to be added or calcium is to be added for sulfide shape modification. Now, the addition of calcium or mish metal has been done in one particular place, for example, in duplex stainless steel, and what they have observed that increase in number of inclusions, also they observed decrease in size of inclusion, decrease in size of inclusions. Now, as a result of both these effect which they have got during inclusion modification by addition of mish metal in duplex stainless steel, they could found that the hot ductility of stainless steel has been considerably improved. Again, in another application, the addition of 0.2 to 0.3% of rare earth metal in steel for drill bit roller cutters, it reduces the oxide and sulfide inclusions in them to change their shape from sharp, angular and elongated to globular and to decrease the grain size. As a result of this modification of inclusions by adding cerium, the strength property and impact strength of cast metal increased, and as a result of that they could modify the inclusions by addition of cerium, and hence the good property has been achieved. So, what I have told you from here, these are the two examples which I have said, but there could be many examples where it is not required to remove all the inclusions, simply just to modify all that you have to find out an element. You can find out several such examples. So, what in conclusion I want to say is that it is not always important to remove the inclusions. However, the bigger size inclusions are to be removed, but the smaller size inclusions, it is not all the time it is required that you remove the inclusions, and but if those inclusions can be modified in terms of their melting point or in terms of their edges, sharp edges or corner edges modified to spherical globule, then it will be good. From application point of view, they will not have a harmful effect.